Now for the fun stuff, an application problem. And this application problem involves a real bridge over the New River in West Virginia. And this is our family went whitewater rafting a couple of times. In both cases, I think we were on the New River, went under this bridge, drove over it. Pretty cool bridge. And this bridge has a parabolic arch in it. So that's a parabola. So we are going to look at some information about this bridge and use it to answer a question. The question we want to answer is this question here. What is the height of the road to the bottom of the arch at the sixth beam to the right of center? So in other words, I want to know how long this beam is. And if I were building a bridge, that would be a useful piece of information to know. I would want to know how long each of the beams are, and I would need to use some sort of mathematical relationship to figure that out. So let's start with, how do we approach an application problem like this? The first thing is we want to draw a graph for the parabola in the problem, and we want to make the graph as easy to work with as possible. So automatically, when we're doing an application problem, think, where's the easiest place to put the vertex? In this case, at the origin. That makes sense. We also want to make sure that we use a scale that is friendly to the problem, numbers that fit nicely with the things we're given in the problem. So let's take a look at some of the distances we're given. We're given, first of all, that this little short distance at the very top of the arch, from the top of the arch to the roadway, is 50 feet. Then we're given that the distance between any two beams is 70 feet, and that the length of the third beam is 80 feet. And that's from the road to the top of the arch. So let's use some of that information to do the picture. So let's think here, if this little short distance at the top of the arch right here is 50 feet, and this is what we're trying to find, we don't want to make each box worth 10, or we're probably not going to have room on our grid to get down to here. So I'm going to make each of my boxes worth 20 in the y direction. So I'm going to just kind of make a little scale that in the y direction, for y, this is going to equal 20. So I need to go up from the top of the arch up to the road, which is 50. So I'm going to draw the top, my x-axis right here, and then my y-axis right down the middle, and have this be 20, 40, 60. So the top of the roadway is going to be right here at 50. So that would be the top of the bridge. Then I want to mark my x direction. So if we look at my x direction, we need to get out to the sixth beam. So I better make each one of my x-axis marks the width of a beam, which is 70. So when I go out here, 1, 2, 3, 4, 5, 6, since they're each 70, the third beam would be at 210, and the sixth beam then would be at 420. And then I can go the same thing in the opposite direction, negative 210, negative 420. So I'm going to make, there's my vertex is at the origin. Actually, I'll do that in black so it's a little easier to see. There's my vertex at the origin. And then I know that the third beam is 80 feet long from the roadway down to the bridge. So 50 feet of that is from the top of the parabola up to the bridge. So this is 50 feet. So I need to go another 30 feet down. And let me mark my axis here. 20, 40, 60, 80, 100, 120, 160, 200. Only those are all negative, obviously. Somebody probably was about to say, half point, half point, half point. Now let me put my point 210, negative 30. And I think I'm going to actually label that because that's going to be an important point that we're going to need to know. 210, negative 30. And then also I would have negative 210, negative 30 over here. And so I could draw my arch kind of going off like so. Now what I want to find out is when we have a beam here at the sixth beam out, how long is that going to be? In other words, where is the parabola going to intersect that line, and how long is that beam going to be? So the first thing we need to do is write an equation for our parabola. And given a point, this is like what we did in the example in the top left-hand corner above, where we picked the equation and then we plugged in a point and figured out what the 4p had to be. So we know that this is facing downward, so it's going to be an x squared because the y is missing, looking for its missing twin. Oh, I can maintain my composure here. So we have an x squared equals 4py, and we know that 4p is going to end up being a negative number because it's upside down. So putting in our known point, which is the point 210, negative 30, I have 210 squared is equal to 4p times negative 30, or 210 squared divided by 30 is equal to 4p. Negative 30 is equal to 4p. And that number turns out to be, pause. Sorry, I couldn't find it well in my notes, but I just found it. That number turns out to be negative 1470 equals 4p. I don't really need to know what the distance to the focus to answer any questions in this problem, so I'm just going to say 4p is 1470, which means my equation is x squared is equal to negative 1470y. So there's my equation. Now, how do I use my equation to answer the question? Well, given an x value of 420, what's y? So I'm going to substitute 420 now in. 420 squared is equal to negative 1470 times y. 420 squared divided by negative 1470 equals y. And that is negative 120 is equal to y. Now, does that mean that the beam is 120 feet? Let's think about that. So let's plot that point, negative 120. That would be down here. So this distance here is 120. And of course, we'd have symmetry on the other side. This would be down here as well. So that would be a picture of our bridge. But the length of the beam also includes this distance up here, which is 50. So we would have to say that the total length of the beam then is 170 feet. So length of the beam equals 50 plus 120 is equal to 170 feet. It's really important when you do a story problem that you use all the tools at your disposal. You aren't just taking a formula and saying, if I plug this number into here, then I automatically get the right answer. That's Algebra 1 baby thinking. You have to think what the numbers mean, look at the graph, interpret the answer, and answer the question. So that's really important. Now, just to show you a cool little thing, I graphed this equation on my calculator using appropriate window settings. And so I have my equation. Let me go back up here. My equation here, negative x squared over 1470, which is the same as x squared over negative 1470. I solved it for y, plugged it into the equation. Then I have another equation that just says f2 of x is 50. That's the road up here. So I just drew the bridge on my calculator. And then I expanded my window settings so that you could see this nicely. And then for funsies, I used the fact that the clearance of the bridge is 876 feet above the water. And so I made a little equation here. Remember that 50, the top of the road, oh, I probably should have made that 876 feet. I was thinking that the top of the bridge was 876 above the water, but probably should have made the bottom of the bridge. Anyway, at any rate, I remember our sinusoidal functions. This would be the sinusoidal axis. I made that at negative 826, and then I had an amplitude of 20, so it would go up and down like this, and I adjusted the period so that the little waves, this is my river down here. I made the river. Isn't that cool? And later on, you're going to have a chance to do a graphing project where you create a picture using graphs. So this is just a little preview of coming attractions. So back, just one more thing to look at is just a reminder that when you approach a story problem, draw a graph, label known coordinates of points. Think about what coordinates you need to find in order to answer the question, and then use your equation, write an equation, use your equation to find those coordinates, and then look back again at the graph to answer the question. So that's kind of the process of thinking you need to do on conic application problems. The end.